So a student is asked to do the part C's from the test, from test one, so I better do that. So question one, part C. So the question what does it say? Produce a pair of scalars C1, C2 such that C1 times U, magnitude C1 times U, so I'll just write this down. So we got U and V are two vectors. I won't write down everything because you should, I presume, have the test in your download. If you don't, get back to me. So you have two vectors U and V. Okay. And the question is, find a pair of scalars, just numbers, such that the magnitude of C1 times U plus the magnitude of C2 times V is equal to 1. Now, there's essentially infinitely many ways of doing this because there's infinitely many pairs, but I thought the easiest thing to do, and it's the solution that one person got closest to, was write U plus V. So U plus V, if you look at it, is 4i minus 3j plus 4k. And then find the magnitude of that. So what you actually end up doing is just finding the unit vector U plus V. So if I find the magnitude of that, we square root sum of the squares. So it'll be 4 squared plus minus 3 squared plus 4 squared, and that gives you square root of 41. And so if you look at U plus V hat, which is equal to 4i minus 3j plus 4k divided by, or actually don't even write that, just write U plus V divided by square root of 41, then this vector here has a length of 1 because it's a unit vector. So what I can do is I can essentially divide the root 41 into both of them. So I get 1 over root 41 times U plus 1 over root 41 times V. And that does the job because that's a unit vector in the direction of U plus V. In other words, it has length 1. Now there's infinitely many ways of doing it. You could have chosen C1, so very easy other options. Pick C1 equal to 0, and then C2, it would just be the constant you need to make V a unit vector. So the magnitude of V looks like root 5. So C2 would be 1 over root 5. That would do it. Or similarly, C2 equals 0. And so that means there'd be no V, and just make the length of U equal to, now we have the length of U, I think in the first part is root 38. So that'd be 1 over root 38. And there's you can actually pick, I think, to a certain extent, I think you can pick C1 and C2 to be almost anything, I think. And there'll be a corresponding value of C2, I think. Yeah, but there's infinitely many solutions. There's two of them. Okay. Now, question 2C. So let's see what question 2C is about. So this was about finding the area of a triangle. So I'll just get to where you should get from the earlier part. So you've got point A, point B, point C, and the actual vectors that are found are not necessarily that useful to you, but you can find the side lengths. You've used vectors to find the side lengths. And so the side from A to C has length root 38. Side from B to C is length root 14. And the other side, AB, has length root 6. Now there's probably other things that aren't vectors that can attack this. But what I'm going to go is I'm going to go for half AB sine C. So I'm going to go for, take a wedge. I'm going to call that theta. And the area, right, area, because there's already an A, is half AB sine C, theta, C there being theta. And so I know A and B are root 6 and root 14, excuse me. I just have to find the angle cos theta. So what I would use to find the angle cos theta is I'd use two vectors, the vector from B to A and the vector from B to C. Now what a lot of people might have done is, so like for example, the vector from B to A is not in the previous parts. So if they used the vector from A to B, they're finding the wrong angle, they're finding an external angle. So we'll just write down this, so the vector BA dot BC is equal to magnitude of BA, which we know, magnitude of BC, which we know, cos of the angle in between. Now what I'm going to do is I'm going to solve this for theta and then put in the numbers. So if I divide both sides by the two lengths, and the cos theta is equal to BA dot BC over the magnitude of the lengths, product of the lengths. And then I can do inverse cos, but I really probably need to find BA and BC at this point. So BA, the vector from B to A, probably the easiest thing here is just to say that that's minus the vector from A to B, and we have the vector from A to B in the question. So this becomes, earlier on, -2, -1, -1. And vector from B to C we do have in a previous part is 3, 1, 2. So maybe we'll do the dot product now. So BA dot product BC is equal to, so -2 by 3 is -6, plus -1 by 1 is -1, plus -1 by 2 is -2. So that's equal to -9. And if I go to the red thing and do inverse cos of both sides, I get theta is equal to inverse cos -9. And I'm going to keep this for the moment. Length of BA is √6 by length of the other bit is √14, because I got that wedge going on. Okay, and now I'm ready to use the formula, and I'm actually just going to keep this expression here. I'm not going to calculate, I'm going to put exactly this into the calculator to get slightly more accurate. So the area therefore is half AB, so that'll be the √6 by the √14, but the sine of the angle in between. So I'm going to put in this thing I just wrote. I'm going to put all this into the calculator. It's just I'm being a bit fussy about rounding error. So like if you calculate theta, there's a bit of rounding error there, and then like you could get something slightly different to what I'm going to get, even though I'm going to go to 4 significant figures now. So √6 by √14 by sine of cos inverse -9 over √6 by √14. And I'm getting 0.8660. And there's no units here, so I can't really say anything. Okay, so that's that. There were other approaches once you found the angle. Okay, and I think there's possibly formulas around just in terms of the side lengths as well for the area, but I was obviously more interested in doing it with vectors. I think question 3C was probably the hardest question on the whole thing. So 3C says that A and B define a plane in space. Do the vectors A and 2A define a plane in space? So this is probably a little bit difficult. So my best bet is probably to draw some pictures. So like even if I just work with I and J, now A and B are not I and J, but what I just want to take two vectors, maybe just to be a bit more, let me just do A and B. So we show that they're not perpendicular. Now we can also show that they're not parallel. So there's something we should write down. So U is parallel to V if and only if one is a multiple of the other, constant multiple of the other. And A and B here are not parallel. Actually, I could have written that a bit cleverer. So write the parallel and then not parallel. And we know that as well because if you do part B, you get a vector that's perpendicular to both of them, or rather you get the cross product. So if A and B are non-zero, this is also the same thing. So vectors are not parallel exactly when their vector cross product is not 0. So if you draw a picture then, and this is where things get obviously a bit more difficult. So say A is like that and B is some other thing. So if you have those two vectors, imagine putting an infinite sheet on them. And in that sense, they define a plane. And in particular, they have a cross product. So you have a vector that's perpendicular to the both of them. And then once you have a vector perpendicular, well, even p hat, which is what we did in this question. Let me just fill in the gaps a bit more just to be absolutely clear. So if you have a vector, you can talk about the plane perpendicular to it. Now there's loads of them. There's loads of them, but I suppose we're talking about this being the origin. Yeah. So actually just put your two arms out in front of you. Put your two arms out and imagine that you can put an infinite, if you put your arms back, start at the same point behind your back somehow. So that's like the vectors A and B. You can put an infinite sheet on them, and so they lie in the infinite sheet, and so you get that A and B define a plane. Now this question is about A and 2A, and I have to kind of try and argue that this doesn't give you a plane. So A looks like this, and 2A looks like this. And the problem is this doesn't define a plane because, so that imagine just putting one arm out and just imagine from your shoulder to your elbow and your shoulder to your arm. So that's kind of, so like A is from your shoulder to your elbow and 2A is like your shoulder to your hand, excuse me. Then there's actually infinitely many planes that they lie in. So if I could kind of go from side on or straight on, so I'll draw the top of this like an arrowhead. So you're looking from this direction is what I'm saying. Well, there's infinitely many planes on there, there, and there, there. There's loads of them. So A and 2A do not define a plane uniquely in the same way. It's a very, very difficult question. There's no two ways about it. So like to maybe answer the question, it's not so easy. No, that is probably too hard. The answer is no. This is just the answer to the question. So there's only one plane that A and B lie in. A and 2A lie in infinitely many planes. So for this one, put your arm out and put a sheet against your arm, and you can rotate the sheet around your arm. So imagine this sheet. So the orange thing is your arm, and you got this sheet, and now you can rotate that around and get loads of different ones like that. Yeah. Okay, not easy, probably too difficult. I fear that. In contrast, question 4C is probably, people should have done better. Okay, so this says the force vector is in the direction of u. So I got a force vector, and that's given in the question. And it says it's in the direction of u. U is not specified, but it says find a vector u such that, the length of u is equal to 2. So find u such that the length of u is equal to 2. So it's actually very easy, because all we have to do is find a vector of length 1 in the same direction as the force and double it. That will exactly do the job. So we'll find the vector f hat by taking the force, which is 8I minus 6j, dividing it by its own length, which should be, I'm fairly sure it should be 10. Let's see, square root of 8 squared plus minus 6 squared, yeah, it's 10, and then doubling it. Because that will now be in the same direction as the force, but it'll have a magnitude of 2. Now there's different things you could multiply into 2, divide by 10. Maybe that's the easiest thing to do. So it'll be 16 over 10i, that's 8 over 5i, minus 6 over 5j. That's all. And question 5c. This was probably easy to get good marks, but difficult to get full marks because it was actually kind of tricky to finish off. So if we draw kind of our picture from an earlier part, so we have force F is at P. Okay, and let's draw the force. Actually, looking at it now, I see an easier way than what I was looking at. And the question is, find a point R such that the moment of the force about R is 0. So the trick here is to realize that if the force is parallel to the displacement, so I could nearly put, I could actually nearly put the point R back here. This makes it quite easy. Well, okay, so I'll put R1 here. Now what that is, and then put R2 back here somewhere. So R1 is, so imagine is like pushing a door. So what I mean by that is, so here's the door frame. So if you push the door, that's like I'm saying that this is the point P and this is the point R1. So pushing the door against the hinge isn't going to cause a moment. And the other one is slightly different. I think it's more like pulling it. So if I go the other way around and have the force going like that away from R2, then that's pulling the door and that's not going to cause a bending moment. So I think the easiest actual answer, maybe the one that makes the most sense for us, is maybe pulling the door. So I'm going to put the R2 back there. And again, there's loads of ways of doing it. The way I did it was very bad in my own marking scheme, but the easiest thing to do is to take R2 to be the point. Now we might have to confirm this just to get it dead right, but I don't think anyone got the answer, and I am going to make the parts easier on the matrices test, to be the point P minus the force. So P is 102 and the force is 2 minus 3, 1. And so I end up with minus 1, 3, 1. Yeah. Now probably what we can do is here we could probably just confirm that. So now if we look at the displacement, so that'll be from R2, which we should really just call R1 at this stage, or just R. So it's the vector from R to P is equal to P minus R. I think we'll see it very easily now. P is the point 102, R is the point minus 1, 3, 1, and that'll give us 2 minus 3, 1. And so the displacement here is actually, oh crap. So the displacement here is actually equal to the force. Now it's totally different units and stuff, so it's certainly displacement is parallel to the force. And if the displacement is parallel to the force, that means the associated moment is 0. Yeah, not so easy. Yeah, so I think the part C's were probably two of them in particular were, let me look back at them. I'm quite happy with the first one, quite happy with the second one. Third one, probably too difficult. Fourth one, quite happy. And fifth one, well, people are getting 4 out of 6 if they just said that they needed to get the new displacement to be parallel to the force. for no moment. So I was happy enough with that. But I think in the matrix test, things are going to be a bit more straightforward.